When you were a kid, did you know you were going to be a physicist and that you'd be working in this kind of setting?
There's no way I could have envisioned this facility, but I love playing with light. I had a laser tag, and rather than playing laser tag with it, I would set up a series of mirrors around the house, and I would align my laser tag to see how many bounces I could get and still hit the target. So that actually was great practice for aligning these complicated optics.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff, with departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others. The college always has something exciting happening. Join us to find out what's new now.
I'm pleased to be joined today by Robert Baker, professor in the Department of Chemistry and Biochemistry at The Ohio State University College of the Arts and Sciences. His research focuses on the critical role that surface electron dynamics and interfacial charge transfer have on the selectivity and efficacy of catalytic energy conversion processes. Dr. Baker, welcome to Voices.
Yeah, thank you, David. Welcome to the NeXUS Laboratory.
I was going to say, you should be welcoming me because
Yeah.
we are right now in the NeXUS Laboratory. First of all, tell us, what is the NeXUS Laboratory? And then you're going to give us sort of an audio tour.
The NeXUS facility is a unique in the nation infrastructure investment by the National Science Foundation. At the heart of the NeXUS facility is a first of its kind laser in the United States that drives the process high harmonic generation. This is a process that was recently recognized by the 2023 Nobel Prize in Physics, which was shared by Professor Emeritus Pierre Agostini
From here at Ohio State,
in our own physics department at Ohio State. And this is a very promising and powerful technology that allows us to produce extremely short pulses of extreme ultraviolet and soft X-ray light that then we use to interrogate electron and molecular dynamics in all sorts of chemical molecules and materials.
Tell us what NeXUS stands for.
NeXUS stands for National Extreme Ultrafast Science Facility. The term NeXUS didn't appear in our original proposal, and when NSF decided to fund this, one of the first things they told us is, okay, we need a great acronym to brand this facility with. And so we actually held a contest amongst the students who were going to help build the facility, and the students actually coined the term.
Well, good for the students. So we're going to walk around the lab for just a bit, but first of all, this is the laser right here.
This is the laser.
So what I'm looking at is, it looks like a bunch of file cabinets laying on the side.
Okay, yeah.
Which is maybe not the most poetic way to describe it.
Right. So this is a CPA, we call this a chirp pulse amplifier, but the laser actually spans this entire length. So see, we have about 15 feet here,
Yes.
and about 30 feet here. This whole thing is the laser. So maybe to give you a comparison, the laser in my lab produces about 5 watts of power, and this laser produces over 800 watts of power.
Wow. So just give a verbal description of what we're looking at here. I gave a clumsy definition of this down here. What are we looking at down here?
So actually, in the boxes that you described as a file cabinet, there's actually 16 fiber amplifiers. Each one of these will amplify a laser pulse. And then there's a very complex interferometer that will coherently combine the output of all 16 fibers to create one massive laser pulse that's firing at hundreds of kilohertz repetition rate. And then as the beam propagates through these tubes, we have several stages of pulse compression. So we can take the output that comes out here at 250 femtoseconds, which is already pretty short, and we compress it down to 8 femtoseconds. And then when we drive high harmonic generation, then we go down to sub-femtosecond.
Yeah, now I recall the last time we spoke, which by the way was 6 years ago.
Okay.
I was checking this the other day.
Okay.
We talked about femtoseconds.
That's right.
Remind us again the kind of scale we're talking about, how fast that is.
So a femtosecond is 10 to the minus 15 seconds. And that was 6 years ago, so now we have a new order of magnitude to describe.
You're joking.
So at NeXUS, we do attosecond science.
Attoseconds?
The attoseconds.
All right, you have to explain what that is.
Atto is 10 to the minus 18, and the comparison that we like to give is there's more attoseconds in 1 second than there are seconds in the age of the universe.
I don't know if I can get my head around this.
Yeah.
So wait a minute, in the 6 years since you and I last spoke, we've got a whole new dimension of time? Is there a new time dimension?
So this is a rapidly evolving field, and as I mentioned, attosecond science was recognized by the 2023 Nobel Prize in Physics. So this has been a field that's been developing for the last few decades, but is garnering a lot of interest because of its potential right now.
And what is that potential? What sorts of work are we talking about
Well,
here?
the reason attosecond is exciting is because this is the natural timescale for electronic motion. Electrons are very light and fast, even compared to, you think, an atom is small and,
Right.
Molecules can react very quickly, but even compared to the atom and a molecule, electron is much lighter and much faster. So whereas molecules react on the femtosecond timescale, electrons move on the attosecond timescale. And so if we really want to understand electronic motion in, say, processes like quantum computing or information processing, where you're flipping charges or spins, which are essentially electronic motion, or solar energy conversion, where you're having to separate positive and negative charges, these are all processes that at their heart are driven by electron dynamics, and these are very fast processes. And so if we want to develop the technology to understand them, we have to be able to interrogate them on the attosecond time scale.
So what does the laser do? What's the laser's role in that process?
So the laser's role is actually to produce the light needed to probe the chemical system of
Which
interest.
is all a laser is, I guess, is light, right?
Well, yeah, a special kind of light, coherent light, where we can tailor the light to the experiment that we're trying to perform. So actually, you'll see the NeXUS Laboratory is pretty large, and we have 3 different beamlines and multiple different experimental end stations. And the goal of every one of these beamlines is to tailor the light in a specific way to enable a unique class of science.
So why don't we take a walk around the lab?
Please. Okay, so the first beamline that you see here, this is for X-ray absorption and X-ray reflection spectroscopy. Some of the applications that would be supported on this beamline would be, for example, studying charge separation in photocatalytic or solar materials, looking at spin crossover in photochemical complexes or molecular magnets.
Spin crossover?
Yeah, so an electron, you think of the electron as a negative charge, but the electron also carries a spin. This is like the fundamental unit of magnetism. So a spin can either point up or point down. Once you compile many of these, this is like the pole and the south pole of a magnet.
Okay.
So, a lot of information processing, a lot of information gets stored as a 1 or a 0. But in many instances, this is a up spin or a down spin. And the ability to flip those basically tells you at what rate you can process information. And so traditional technologies might flip spins on like the nanosecond time scale. But okay, could we go 6 orders of magnitude? Could we go 1,000,000 times faster and flip spin on the femtosecond, or 9 orders of magnitude faster and flip spin on the attosecond time scale? These are the questions that we want to ask at NeXUS.
Any answers yet?
Any answers? Well, there are some very exciting results that are kind of being published in the last few years that suggest that we have not yet reached the fundamental limits, and that attosecond processing is definitely possible, and that's why scientists are excited to come and use this facility. Let me take you to the next beamline. So this second beamline actually tailors the light in a different way that supports what we call ARPES, that stands for angle resolved photoemission spectroscopy. This allows you to see the band structure, or in other words, the way electrons distribute their energy and momentum in materials. So there'll be a lot of surface science that will happen at a beamline like this, studying things like quantum materials, 2-dimensional materials, transition metal dichalcogenides. So this is kind of like a very material science focused beamline and end station.
What sorts of results?
This is something that's unique about NeXUS is, unlike my laboratory where I get to choose the type of science that we do, the NSF invested in this infrastructure in order to make this sort of technology that we specialize in here at Ohio State broadly accessible to the entire community. So scientists from around the country or around the world will have the chance to submit their best ideas. These will be reviewed, and those that are selected for time will get to come and perform their experiments. So we have exciting ideas, but really what NSF wants to see is that the entire community is going to define the science that happens here. And toward that goal, we're actually hosting a users workshop next week where people from around the country will come. We'll be brainstorming together and discussing the exciting first scientific experiments that are going to happen as NeXUS opens this fall and in the coming year.
How many people are you anticipating?
We are going to have probably 70 people in person, and then a much broader audience tuned into some of the plenary talks online.
I'm noticing, and you'll excuse me, that looks like tin foil at the end of this. Surely
Yeah.
that's not tin foil.
Well, actually,
Aluminum foil.
That's aluminum foil, and aluminum foil comes in very handy in
like I'd find in my kitchen.
Yeah, aluminum foil is very clean and doesn't have any of the greases that we have in our fingers. And when you're doing experiments like this, surface science experiments, where you need extremely low pressures, you don't want grease or dust on anything. So any open ports that are temporarily exposed to air, we wrap them up in aluminum foil to keep them pristine. The last beamline is for an experiment where we'll couple XUV light to an STM. STM stands for scanning tunneling microscope. Scanning tunneling microscopy is a technique that allows you to get subatomic scale spatial resolution. So you can actually resolve single atoms on the length scale of less than an angstrom.
When you say resolve,
I mean, you
like
can actually
picture.
look. You can actually take a picture, look at a photograph that shows individual atoms and even electron wave functions, which are smaller than the atom itself.
That's extraordinary.
So this is a really challenging technique, but very powerful technique. One of the traditional limitations of this technique, though, is although you can take the image of the atom, it's hard to know exactly what you're looking at. So you can't tell one atom apart from another. And this is where the light will play a critical role, because if you do this measurement, but now you do it under illumination of our soft X-ray light, and you can tune this light to go above and below a specific transition that's unique to a certain element. Now we can kind of impart a contrast, or in other words, we can make every different element in the image pop out at a different color. And so now you not only see the spatially resolved image, but now you can know exactly what atom you're looking at.
I can imagine what the uses are, the value of this. I mean, aside
Sure.
from pretty pictures, how
Yeah.
will physicists be using these?
Well, so if you think about solid state devices, you often have to put dopants into a semiconductor. A dopant, okay, this could be like phosphorus in silicon or boron in silicon. You have this in your phone. This is in the microphones that are clipped to our lapels. This is how we process information right now, is by electronic circuits that are built out of doped semiconductors. But then it's often hard to actually go down to the scale of an individual dopant atom in a semiconductor and actually see how are the electrons moving at that specific atomic site. That's the sort of measurements that we'll be able to do at this end station.
I can't even begin to describe how intricate and complicated this is. And I suppose the question I have is, who built this?
Well, impressively, this was built by graduate students, postdocs, and research scientists here at Ohio State University.
You have to describe that process. I wouldn't even know where to begin.
Well, this is really an incredible story, because when we first envisioned this facility and began writing the proposal to the National Science Foundation, this was in 2018. And we were one of 9 mid-scale facilities selected for funding in the inaugural year of this infrastructure program, which was 2019. And before we could even kind of finish celebrating receipt of this award, COVID hit, and we went into lockdown.
Yeah.
And so basically our team was tasked by taking relatively young graduate students and some postdoctoral scholars and trying to work remotely and begin the monumental task of designing this. This existed in AutoCAD before any of these vacuum chambers or wires or feed-throughs were ever fabricated. And this all happened during the last 5 years, thanks to the devoted efforts of some really talented students and postdocs.
Who designed that? Who created the AutoCAD version of this?
Well, this was done by the students, postdocs, and outstanding research scientists that we
just
have
all of
here
them.
at Ohio
It's just
State.
amazing.
Yeah.
And so, is that part of one's training as a physicist? In other words, are you trained to also be a construction engineer?
Well, you have to wear many hats when you take on an endeavor like this, but that's actually one of the things that motivated this program from the perspective of National Science Foundation, is they recognize the importance of workforce training to be able to construct instrumentation and design these very cutting-edge experiences. And actually, this is an area where the United States has traditionally lagged behind Europe and other countries in investing in this sort of infrastructure. And so one of the things that the National Science Foundation finds attractive and that we're really proud of here at Ohio State is that this facility is providing that type of workforce training to students here.
When you say workforce, what other sort of applications outside of this laboratory, outside this university?
The laser, which is the heart of the NeXUS facility, the place where it finds its biggest application is on manufacturing floor. So these really high average power ultra-fast lasers have a lot of applications, and some of these are in laser processing and machining and fabrication.
Why does the U.S. lag behind Europe and other areas?
You know, there have been a number of reports. So there was a landmark report that got published in 2018 called Reaching for the Brightest Light. This was a report by the National Academies of Science. Lou DeMauro, who's professor of physics department, played an important role in this. And one of the things that these reports have documented is that in the United States, we have a certain funding platform which does a very good job of funding individual principal investigators like me and my own research laboratory and many others here at OSU. And it also does a good job at funding large-scale facilities like synchrotrons, the X-ray free electron laser at SLAC. So we're talking about large DOE facilities. But
Department of Energy.
Department of Energy facilities. But between these two extremes, there's a gap, which NSF has titled mid-scale research infrastructure. So this refers to things that are bigger than a single PI laboratory, but still much smaller than like a $1 billion investment by the Department of Energy in a synchrotron facility. And so this is something that in other countries has been part of the culture of science and built into the funding portfolio. And in the United States, we kind of recognize that this has been lacking. And so the NSF and other funding agencies have been very enthusiastic at responding to these reports. And this is one of their responses. And so in the way, it creates a new paradigm for science here in the United States, which is highly collaborative. So for example, I'm not necessarily an expert at quantum information processing, but I am good at designing femtosecond and attosecond light sources. So what can I do in collaboration with the material science expert who has very promising material for quantum information processing, but they need to understand electron dynamics in this material. And so we envision this being like a center point for interdisciplinary collaboration where we provide the light and the local expertise to operate this very complicated infrastructure, but people come from all over with their own scientific questions, and they're going to help us define what science we do here.
So that's what you meant by mid-scale. I was going to ask you that question.
Yeah,
what's meant by mid-scale?
Mid-scale, so we're bridging this gap between something that's too big, too complicated for me to do with just my own few graduate students in my own research laboratory. It takes the investment of an entire community, but still is not the construction of a full DOE national laboratory.
And maybe you indicated this earlier. Why was Ohio State chosen for this?
Yeah, well, that's a great question. I think Ohio State was chosen largely because we have a great team here that provides the local expertise. So the National Science Foundation wants to put this in a place where the host institution, Ohio State, can support the user community of being successful at these experiments. We need the local expertise. So this is a place where we have long-standing expertise in attosecond science, the Pierre Agostini DeMauro Laboratory that is recognized by the Nobel Prize. We have Roland Kawakami and Jay Gupta in physics, who are experts in their ARPES and STM measurements, Claudia Turo in chemistry, who's a renowned photochemist, and our expertise in the light sources. So we provide the local expertise and support that NSF thinks is going to be critical to supporting the users that will come and be here at NeXUS with us.
Tell us what NeXUS stands for. I probably should have asked you that at the very beginning.
Yeah, that's a great question. So NeXUS stands for National Extreme Ultrafast Science Facility. So actually, NeXUS, the term NeXUS didn't appear in our original proposal. And when NSF decided to fund this, one of the first things they told us is, okay, we need a great acronym to brand this facility with. And so we actually held a contest amongst the students who were going to help build the facility. And the students actually coined the term.
Well, good for the students. So you and I are wearing lab coats. I'm wearing a hairnet. I'm also wearing a beard net. And I obviously I don't wear a beard, but I am a couple of days scruffy here. Why am I wearing all of this?
Yeah, so NeXUS is a clean room. There are some optics which are exposed to air, and they're illuminated by this very high intensity light. And so any dust that could land on these optics would irreparably damage them. Some of them are extremely expensive. They have long lead times. And basically to protect this highly sensitive equipment, we keep dust in this room to an absolute minimum.
I am not wearing the goggles that I saw.
Okay.
Those are outside as we were getting dressed.
Right.
And maybe it seems self-evident. Why would I have to wear goggles in here?
Well,
and they're special goggles.
They're special goggles. When the laser's on, you for sure need to have the laser glasses on because, as I mentioned, this is a really high power laser. I mean, first of its kind in the United States. So the goggles that you wear have interesting colors. These are specifically designed to protect your eyes from the different wavelengths that might be out on the experimental table during the course of any given experiment.
Yeah. And in fact, you actually wouldn't allow me in here, I'm guessing. I'm not certain I would want to be in here.
Yeah, I'm not sure you would want to be in here if the laser were operating, but we have some really talented and well-trained staff. And so, it's under their supervision that the laser is operated.
Tell me about your involvement in this. Why were you involved in this whole process? You say it's a collaborative effort.
Right.
Why Robert Baker?
Well, my group had the opportunity to be involved in pioneering some of the techniques that we're now making accessible to the community. So in a sense, to me, this is a community validation of the potential impact of the sort of techniques that we've been working hard to develop in my laboratory. Basically utilizing this type of light to make measurements in photocatalytic and solar materials, and kind of demonstrating to the community how powerful these types of measurements can be in terms of understanding what are the real physical processes that control the performance and efficiency of this really important class of materials.
You mentioned graduate students and others who worked on this, and obviously the research implications are immense. This in no way is involved in teaching. This lab is not involved in teaching, or perhaps it is.
Well, not in the classroom sense. So we don't host undergraduates here, although we have had some undergraduate researchers contribute in some important ways to the development of the facility. But no, this is more of a laboratory setting where you're really getting very unique training and experience in exposure to instrumentation and lasers and experiments that are really only done at a handful of places worldwide. So I'd say it's more of a laboratory training experience where the people who work here come out with unique skill sets that probably only a few places in the whole world can provide that sort of training to students.
What's the research horizon look like? What are you going to be working on going forward here?
Our goal is to show the power of this facility to the research community. So, what I would consider a great success is that in 6 months or a year from now, the NeXUS facility becomes oversubscribed, meaning that there are more people wanting to use the facility than we could possibly accommodate. This would send a message to the funding agencies that this was a great investment and that more of this type will be needed in the future to meet the scientific demand.
How will those decisions be made?
Yeah, so that's something that we're discussing with the NSF right now, but they want to see that this is a really open and accessible and transparently operated facility, and that's done with the help of user committee, a really high quality scientific advisory board, a lot of strong institutional support from the university. It's incredible the number of people supporting this in various ways to make this successful.
What's the organization of the lab? Is there a CEO?
There's no CEO, but there's a director. I'm the director as we transition to operation and maintenance. Lou DeMauro and I were co-directors during the construction phase of this facility, and there's a facility manager who's TJ Ronigan. And then we have our research scientists and staff. I told you that we involved a lot of graduate students and postdocs.
Yes.
That was during the construction of this.
Right.
Now that this opens as a user facility, now the role of graduate students and postdocs will be to propose experiments and do experiments here. But NeXUS is really what it's going to employ as a full-time staff of dedicated scientists and technicians who are qualified to operate the equipment, support the users, and then faculty, students, postdocs, and researchers from around the world will now be the proposers. They'll be the science drivers. They'll write the proposals. They'll come and collaborate with our scientists and staff here to make the experiments a reality.
What's your job as director?
My job as director is to make sure that the facility serves the needs of the user community and make sure that the science we're pursuing is really high impact, that basically we meet the vision that kind of motivated this investment 5 years ago.
And probably looking for more funding as well, I suspect.
Well, I think that is forthcoming. The NSF has been a strong supporter of this, and they've communicated that this sort of mid-scale research infrastructure is going to be key to their portfolio moving forward. So I think this is the beginning of a long partnership between Ohio State and the NSF.
Now that the laser is installed and operational,
Yeah.
What's next? What else is going to be added to this lab? Although as I'm looking, I don't know if there's much space here. But are you thinking about those next steps?
Well, yeah, definitely. So as you can see, this lab is full. So
It's pretty full.
right now, what's our highest priority is to actually now use the recently installed laser to actually demonstrate the experiments that this was designed to support. And then, of course, we're interested in growing the facility and offering the next generation. I mean, the National Science Foundation and of course us here, we want to see NeXUS stay at the cutting edge. As I mentioned, this is a rapidly evolving field, and so what the cutting edge looks like today is going to look different 5 years from now. And so we have the benefit of being at the very tip of this field, and okay, it's going to take a lot of creativity and hard work, but I think the next 5 years is going to be exciting.
I can't recall if I asked you this the first time I interviewed you. When you were a kid, did you envision yourself doing this? Did you know you were going to be a physicist and that you'd be working in this kind of setting?
There's no way I could have envisioned this facility, but I love playing with light.
Is that so?
Well, I remember I had a laser tag set when I was a kid. And rather than playing laser tag with it, what I would do is I would set up a series of mirrors around the house, and I would align my laser tag to see how many bounces I could get and still hit the target. So that actually was great practice for aligning these complicated optics.
I was going to say, when I think of laser, when maybe the listeners think of laser, maybe they're thinking of something like laser tag, or
Right.
My son used to have a board game that involved laser, which is really not what we're
It's not
talking
that
about
different.
here.
I mean, it looks pretty complicated. There's a lot of stainless steel, but if you follow it, these mirrors and optics, they direct the light from its output at the primary laser, they tailor it, they shape it in time and space, and they deliver it to the experimental end station. So in a way, it's not dissimilar to the mirrors I used with my laser tag set growing up.
How is NeXUS going to impact the university? What departments are going to be impacted by the existence of this lab?
Okay, that's a great question. So NeXUS is very broad scientifically. So it touches a lot of different fields of science, and we want to create a collaborative research environment here. So NeXUS touches chemistry, it touches physics, it touches material science, it can answer important questions about ultra-fast processes and biological systems. And so this is an endeavor that spans many fields of science. It touches multiple colleges at the university. The College of Engineering, the College of Arts and Sciences is the home to NeXUS and has been a strong supporter from day one. We have support from the Department of Chemistry and Biochemistry, the Department of Physics, but even chemical, biomolecular engineering, material science and engineering, computer science and engineering, material science and engineering. These are all fields that can really benefit from the tools that NeXUS provides.
Robert Baker,
Okay.
Thank you for inviting us into your lab.
Thanks so much, David. It's great to host you here.
Voices of Excellence is produced and recorded at The Ohio State University College of Arts and Sciences Marketing and Communications Studio. More information about the podcast and our guests can be found at go.osu.edu/voices. Voices of Excellence is produced by Doug Dengler. I'm Jen Farmer.